Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. And imagine a sphere 12 miles wide that weighs twice as much as our sun. A teaspoon of this substance would outweigh Mount Everest. This is a neutron star, the dense, rapidly spinning remnant left behind after a massive star collapses in a supernova. When we think of a celestial body this extreme, we usually imagine chaos, a seething, unstable monster of gravity. But hidden beneath the atmosphere of this monstrous object is one of the most astonishing examples of order in the entire universe. A perfectly solid, flawless crust. Astrophysicists sometimes refer to it metaphorically as a glass planet. It is, quite literally, the smoothest, strongest, most perfect crystalline solid known to existence. But how does the universe create such perfection under the most violent conditions imaginable? And what exactly is this hyper-solid crust made of? First, let's understand the structure. A neutron star isn't homogeneous. It has several distinct layers. At the very top, there's a thin, gaseous atmosphere. Below that is the outer crust, which is where the magic of solidity begins. This crust is not made of the standard elements you find on Earth. It is primarily composed of heavy, highly stable atomic nuclei, mostly iron-56, stripped entirely of their electron shells. Non-Earth matter is governed by chemistry and electromagnetism. Atoms bond to form molecules, creating liquids, gases, and solids, all of which contain defects, like tiny cracks, voids, or misaligned crystal boundaries. These flaws limit the strength of any material we can engineer. The situation is profoundly different inside a neutron star. The gravity here is absolutely staggering, about 100 billion times stronger than Earth's. This immense pressure acts as the universe's ultimate forging tool. Under these pressures, the ions, those heavy, bare iron nuclei, are forced into the lowest possible energy state. They arrange themselves into an unbelievably uniform, ordered three-dimensional lattice. Think of it like a perfect, flawless crystal that spans the entire surface of the star. What prevents this perfect lattice from shattering? It's held together not by chemical bonds, but by a sea of free electrons, forced into a state known as electron degeneracy. In this quantum mechanical state, the electrons resist further compression with phenomenal force. They act as a hyper-dense, non-compressible glue, locking the heavy nuclei into place. Non-Earth. If you cool a liquid slowly enough, you get a highly ordered crystal. If you cool it rapidly, you get amorphous glass, disordered but smooth. The neutron star crust is neither fully typical crystal nor typical glass. The gravity provides the pressure equivalent of perfect, eternal annealing, ensuring that no thermodynamic defects, grain boundaries, or irregularities can form. Any deviation from perfect arrangement would require slightly more energy, and gravity instantly crushes the material back into its lowest energy state. This results in a material that is theorized to be 10 billion times stronger than steel and incredibly smooth. Its surface irregularities, the difference between the highest peak and lowest valley, are estimated to be less than 5 millimeters across the entire 12-mile span of the star. It is a mathematically smooth object, practically a giant, polished glass marble suspended in space. This mechanical perfection has major consequences for the neutron star's behavior. When a neutron star spins down slightly, the stress builds up in this incredibly rigid crust, much like stress building up in a strained spring. When the tension finally exceeds the crust's impossibly high breaking point, it fractures in an event called a starquake. These starquakes are so powerful they release energy equivalent to the sun's output over 100,000 years. manifesting as giant bursts of X-rays and gamma rays. And below this outer crust, the bizarre geometry continues into what is famously known as nuclear pasta. Here, the density becomes so extreme that the pressure forces the nuclei to merge and deform into elongated, complex shapes, like spaghetti, lasagna, or gnocchi, before dissolving entirely into a liquid core of pure neutrons. But on the surface, that thin, hyper-solid shell remains the ultimate testament to order under pressure. It is the perfect crystal, the glass planet forged in the death of a star. And for more incredible facts like this, don't forget to subscribe and turn on notifications.